Let's discuss a problem about torque and the time derivative of angular momentum. So consider a particle with mass 0.5 kilograms that moves along a straight line with position given by the following position vector, where r is in meters and t is in seconds, and the motion is starting at t equals 0. The position vector points from the origin to the particle, and so in unit vector notation, find expressions for the angular momentum L of the particle and the torque T acting on the particle, both with respect to the origin. Here I'm going to use the relationship between the position vector, the linear momentum of the particle, and the angular momentum, and that relationship was given by the cross product of the position vector r and the linear momentum p. So the angular momentum of the particle is equal to the cross product of r and p. Once I find the angular momentum, I can then use the relationship between the torque that's acting on the particle and the angular momentum of the particle. And so the torque is equal to d dt of L. So the angular momentum is the cross product between r and p, which also can be rewritten as m times the cross product of r and v, where v is the velocity of the particle. That means that I first must find what v is equal to. Before I do the calculation, let's quickly discuss what's the actual physical situation in the problem. How is the particle moving in space? Where is the coordinate system? Where is the position vector? So here's my coordinate system. Horizontal x-axis with positive orientation to the right. Vertical y-axis with positive orientation vertically up. On both axes, the distances are measured in meters. Here is my particle with mass equal to 0.5 kilograms, and this is the position vector r that defines the position of the particle in space. So the statement of the problem states that when the particle, at time t equals 0, the particle is, the motion starts when the time is equal to 0. That means that the particle is at this position right here, which would be 5 meters. And so the progression with time would be the particle moving along a straight line and the position defined by this position vector. Okay, so to find the velocity of the particle, I simply must take the time derivative of the position vector. So the time derivative of the position vector gives me minus 4t minus 1 I hat meters per second. That's the velocity of the particle. Now to calculate the cross product between the position vector and the velocity vector, let's remember how do we calculate a cross product. So for two vectors a and b, the cross product of a and b by components is equal to this sum of three terms. We've discussed this towards the beginning of the semester, so if you are having trouble remembering how to get those terms, please go ahead and review the handout that I gave you on vector multiplication, specifically the cross product. So I added the position vector right under the velocity vector. Now let's see what components are present here in both vectors. So for the velocity vector, we only have the x component. The y and z components are 0. And for the position vector, we only have the x and y component, and the k component is 0. So that will help me to eliminate the unnecessary terms in the sum here for the cross product. And I can get a much simpler version of the result here without going through all the steps. So here are the coefficients for the here are the x component, y and z components of r, and then the x component, y and z component of v. So substituting everything in the expression for the cross product, I get 0i plus 0j plus 4t plus 1 times 5k. Or that is equal to 20t plus 5 k hat, and the units will be meters squared per second. Now to find the angular momentum, I simply must multiply the previous result by the mass of the particle. So that is 0.5 kilograms times 20t plus 5 k hat meters squared per second. The final result is that the angular momentum as a vector is equal to 10t plus 2.5 k hat. The units will be kilograms meters squared per second squared. I must correct, the units here will be kilograms meters squared per second, not meters squared per second squared. To find the torque that's acting on this particle, I simply must take the time derivative of this expression for the angular momentum. So the torque is equal to ddt of L, or that is ddt of 10t plus 2.5 k hat kilograms meters squared per second. Only the first term in this expression is time dependent, so that's the only term that will survive the derivation. The final result is that the torque is equal to 10 k hat kilograms meters squared per second squared. If you look at the result for the angular momentum L, this is a positive coefficient times k hat, which means that the orientation of this vector is along the positive z-axis. So if you remember, the definition of cross product involves the use of the right-hand rule to determine the direction of the resultant vector. So if I apply this right-hand rule in the example here, how do I get the direction of the angular momentum without knowing any values, without doing any calculations? So here is my x-axis with positive orientation to the right. Here is my y-axis with positive orientation vertically up, as we see it on the board. And then the z-axis is coming out of the screen or out of the page, pointing towards me. So the position of the particle in space is given by the position vector r, and then the velocity of the particle is parallel to the x-axis in negative x direction. So to apply the right-hand rule, I will slide the velocity vector so that both the position vector and the velocity vector start at the same point. And for simplicity, I'm going to consider the moment when t is equal to 0 seconds. So at t equal to 0 seconds, the particle is located on the y-axis. So if I slide the velocity so that both the position vector and the velocity vector have the same origin, now the right-hand rule tells me that if I place the fingers of my right hand in the direction of r and rotate towards v, like so, then the angular momentum vector will be along the direction of my thumb. And so the angular momentum vector will be pointing out of the screen towards my face. So that's how we can determine the direction of the angular momentum using the right-hand rule. So if I were to do calculations with that value, I know that it is along the positive z-axis, so therefore I'm going to take that into account by adding a plus sign in front of the value. If the orientation was in negative z direction, then when I do calculations, I would take the value with a minus sign to account for the direction.